Artificial intelligence represents a diverse and evolving field encompassing multiple classifications, technological domains, and computational approaches. It is no longer speculative, but a practical force reshaping economies, institutions, and everyday life. Understanding its foundations is essential for academic analysis and applied implementation, as these foundations define both technical capacity and societal implications. While public discourse often highlights futuristic scenarios, the most consequential developments today arise from narrow and task-specific systems embedded across critical sectors. Artificial intelligence can be analytically distinguished into three principal classifications. Narrow artificial intelligence refers to systems designed to perform specialized tasks within clearly defined parameters. These systems may surpass human performance in limited domains, yet lack general adaptability. Digital assistants, recommendation engines, and automated diagnostic tools exemplify this category, which constitutes the dominant form of contemporary deployment. General artificial intelligence denotes systems capable of reasoning, learning, and adapting across a broad range of intellectual tasks. Unlike narrow systems, general AI would demonstrate cross-domain transfer of knowledge and flexible problem-solving capacity comparable to human cognition. Despite significant research investment, this classification remains largely theoretical, with ongoing debate regarding feasibility and governance implications. Superintelligent artificial intelligence represents a further conceptual extension. It describes hypothetical systems that would surpass human intelligence in reasoning, creativity, and potentially emotional interpretation. Although speculative, discussions surrounding this category influence long-term ethical and regulatory frameworks. Debates concerning autonomy, control, and societal impact illustrate how theoretical classifications shape present governance discourse. Beyond classification, artificial intelligence is constituted by core technological domains that operationalize computational principles. Natural language processing enables interaction between humans and machines through text and speech. By analyzing linguistic structures and contextual meaning, these systems support translation services, sentiment analysis, conversational agents, and automated content generation. In applied settings, natural language processing enhances institutional outreach and access to information. Computer vision equips machines with the capacity to interpret visual data. Through pattern recognition within images and video streams, systems can detect objects, identify anomalies, and assist navigation. Applications range from medical diagnostics to agricultural crop monitoring. Automating visual assessment enhances efficiency and supports earlier detection of critical conditions. Robotics integrates artificial intelligence with mechanical systems to perform physical tasks in dynamic environments. In healthcare and disaster response, robotic systems automate repetitive procedures, assist logistics, and extend services to regions facing personnel shortages. The fusion of computational intelligence with embodied mechanisms expands the operational reach of automated systems. Expert systems constitute another foundational technological domain. These systems encode structured, rule-based knowledge to replicate human decision-making in specialized contexts. By applying predefined logical frameworks, expert systems provide preliminary legal guidance, medical triage recommendations, or technical troubleshooting support. Although less adaptable than machine learning systems, they remain valuable where predictability and interpretability are essential. Underlying these technological domains are core computational techniques. Rule-based systems operate through explicit conditional logic, applying predefined instructions to structured scenarios. Their transparency ensures predictability, but limits flexibility in ambiguous or rapidly evolving environments. Search algorithms enable systematic exploration of solution pathways within defined problem spaces, employing structured traversal or heuristic optimization strategies. As problem spaces expand, computational complexity increases significantly. Managing scale and ambiguity becomes a central technical challenge. Knowledge representation methods address this challenge by structuring how information is encoded and processed. Semantic networks, ontologies, and structured data frameworks allow systems to organize concepts and infer relationships, enabling logical reasoning across domains. Applications across sectors demonstrate how classifications, technologies, and techniques converge in practice. In healthcare, artificial intelligence supports diagnostic processes through analysis of medical imagery and patient data. In agriculture, predictive models optimize irrigation schedules, forecast yields, and detect pest patterns in environmentally variable regions. In education, adaptive learning systems tailor instructional content to individual learner profiles, addressing disparities in access and engagement. In financial services, machine learning-driven credit assessment expands access to microfinance by evaluating alternative data sources. These applications illustrate the transformative capacity of artificial intelligence when aligned with concrete challenges. However, successful implementation depends on foundational conditions. Data quality remains central, as biased or incomplete datasets can distort outcomes and reinforce inequities. Computational infrastructure and technical expertise influence feasibility, particularly in low-resource contexts where hardware capacity and training opportunities may be limited. Ethical governance frameworks must therefore accompany technological adoption. Fairness, transparency, and accountability are not optional considerations, but structural requirements. Narrow artificial intelligence currently offers the most feasible and scalable benefits, especially when deployed through carefully defined, problem-specific initiatives. Incremental adoption supported by contextual adaptation strengthens sustainability. Organizations seeking integration must combine accessible tools with local capacity building. Cross-sector collaboration between academic institutions, technology developers, and community stakeholders enhances both legitimacy and long-term viability. Artificial intelligence fundamentals, its classifications, core technologies, and computational techniques form the conceptual basis for understanding present capabilities and future trajectories. While speculative categories frame long-term ethical debates, contemporary impact is driven primarily by narrow systems embedded in everyday operations. For scholars, ongoing inquiry should examine the societal implications of these foundational structures. For practitioners, responsible implementation requires incremental deployment, ethical vigilance, and sustained investment in human expertise. By aligning technological innovation with governance responsibility and contextual awareness, artificial intelligence can function as a mechanism for inclusive and sustainable development. Understanding its foundational architecture is therefore not merely technical preparation, but a prerequisite for equitable and informed deployment.